Okay, thank you everybody. And so our second speaker today is Patrick Kidger from Oxford, who's going to talk about neural controlled differential equations for irregular time series.
All right. Hello, everyone. Thank you very much for the opportunity to speak. As the title suggests, this is going to be about neural CDEs. So this is joint work with my co-authors, James, and Terry. Now, what's a quick summary of what's going on here? We introduce a new state-of-the-art machine learning model for time series, and it's based off of the language of controlled differential equations, which we all know and love. And it's inspired by existing work on the neural ordinary differential equation model. And also, I should add, by the way, I'm assuming that people are probably reasonably familiar with controlled differential equations, but I'm not going to assume any familiarity with neural differential equations. And so on that note, as a result, quick recap. For supervised learning, right, we want to learn some map from some object X to some object Y, or between pairs of such objects, by learning some F, such that Y is approximately F of X. And then the neural ordinary differential equation model is essentially going to impose an ansatz for F. So we have the same goal as before. And now we're going to decompose it into these three pieces, F, L1, and L2, such that we have this initial condition, which is this function of our input X. And we're now going to evolve Z according to this ordinary differential equation with vector field F. And then eventually, when we get to some essentially arbitrary terminal time, capital T, then we're going to project down this Z, and then we're going to ask that this then resemble our desired result Y. And Z is now referred to as the hidden state. And this is completely analogous to the hidden state of, for example, feed-forward or residual networks, where in such networks, as you go through layer by layer, then the hidden state changes, right, as you go through each hidden layer. And here, the hidden state is changing as it's affected by the vector field as we solve the differential equation. And the reason these are kind of cool is that they have this efficient training algorithm called adjoint backpropagation, where normally, if you have this time horizon capital T, then you expect to have to use order T amount of memory to record everything that happens on your forward pass, so that then subsequently, when you want to propagate your errors in the backpropagation and the backward pass, you can then work your way backwards through the computation. And if, for example, if you were to solve this differential equation just using an ODE solver, then you could then record everything you do and then just backpropagate through the internals of the solver, and that would have this order T. But because it's a differential equation, it's actually possible to solve it backwards in time and reconstruct where you were before. And as a result, this means you don't need to store these things in memory, and you end up with this order 1 memory property. For this concern about stability, yes, that is actually an issue here, and that's not what I'm going to discuss. Okay, so none of this has so far mentioned time series. I've just had some general objects, X and Y. And so very common, if you have a time series, you've probably seen recurrent neural networks pop up. You have some sequence xi, and then we're going to try and learn some map from the sequence by learning some f and some l, such that typically the first z naught is 0, although there are other options. And then we iteratively, recursively define this sequence, zi plus 1 is f of zi and xi. So we keep feeding in elements of our sequence and the previous z to compute the new z. And then finally, when we get to the last hidden, this last z, then we can project that down and ask that this look like y, or if y is sequence valued, then we can do this for every element z. And once again, z is hidden state. Okay, so far this is sort of probably quite standard. So how do we apply neural ODEs for time series? So that's the equation for a neural ODE that we've already seen. Now, this integral over S that we've introduced, this is introduced and integrated over. It's just some internal detail of the model, and we never, we don't really get the opportunity to use time series data here, right? If we have some ordered data like this time series, what we'd like to do is somehow align our new introduced dimension with the ordering of the data. But the problem with this is that this ODE, and that an ODE, the solution to an ODE, is determined by its initial condition. So if we're doing this alignment, then our initial condition is going to be some function of this first piece of data x0, and then there's no way to incorporate this later information, x1 up to xn. So previous work on this has introduced the Ode Rnn model. So if you recall the equations for an Rnn, put them up at the top again, then the Ode Rnn model says, okay, we'll start with some hidden state as before, and I've now got this little plus there. Then I'm going to define my next hidden state according to this recurrent update. But now what I'm going to do is in between these updates, I'm now going to update my hidden state again according to a neural ordinary differential equation. So as a result, we're interleaving these recurrent and neural differential equation steps. And then once again, as before, we have some readout at the end. So as a picture, it looks something like this. We've got some data x, some process x, which we observe at these values, xi. And every time we make an observation, then we have this recurrent update. And in between observations, we evolve according to some differential equation. And the amount of time we evolve for is going to correspond to the sampling of our data, which may be irregular. So it's for different amounts of time each time. So up until now, these have been essentially the state-of-the-art model for many time series problems. I think I probably encourage you to think of this Ode Rnn model as a neural jump ordinary differential equation. It's just this one ODE where every time we see some observation, we reach into the hidden state and make a jump. But the problem with this is that by having made a jump, we've broken the adjoint backpropagation. It's not possible to backpropagate across the jump because once we're on one side of it, we can't recompute where we were before. And so with this essentially is the starting point of existing work. This was really the motivation for, can we try and fix this somehow? And this is where neural CDEs enter the picture. So once again, we're going to assume we observe some sequence X. And now for completeness' sake, I'm going to assume this is irregularly sampled. And it has these timestamps, TI, at which we observe each XI. And I've not mentioned this in my notation, but if you like, you can imagine that some of the values in XI may also be missing. We may have missing data here. At this point, what we can now do is just the similarity of notation with earlier. And then we're going to essentially just join up the dots with this natural cubic spline. So very often, as you've in that previous picture, right, we had this data process X, which we are observing and sampling at these times Xi. And this natural cubic spline interpolation is now going to be our best guess approximation to this otherwise unobserved underlying process, this data process. The choice of natural cubic spline is actually a meaningful one that is important. And if I get time at the end, I might get time to discuss why that is. But for now, this should hopefully feel like a plausible thing to try doing. Okay, with this in hand, we're now going to try and learn our map as before from some time series. And now we're going to do it by learning zeta, f, and l, such that we have some initial condition, which is a function of our first time point. And then we're going to evolve according to this controlled differential equation. And so in particular, as you can see inside this differential equation, this is a Stilcher's integral, and we have this matrix vector between f and dx. And then, very much as before, we're going to either have some readout either at the end for y, or if y is time dependent, then we can ask that we read out all the way along. So for example, this gives us a way of doing sequence-to-sequence models. So as you can see, what we've essentially done is just parameterize the system of a CDE by a neural network. I think it's worth mentioning here that this is somehow like the inverted case to how one very often considers control problems, where very often one assumes that the system is somehow fixed, and now we want to try and use this ability to control the control to get a desired response in Z. But here it's the other way around. Our control, capital X, is given to us, that's determined by data, and instead we're going to try and change our system, F, so as to provoke a desired response in Z. And once again, Z is his hidden state. This is analogous to the recurrent neural network. And so if those are the equations for neural CDE, once again, then this is what it looks like as a picture. We have our data process X as before. We observe it at these values Xi. We join up the dots to create this path, capital X, and this then modifies our hidden state in continuous time. And so I invite you to compare this to the picture of an Ode Rnn that I put up earlier, which in this case is instead making these discrete updates every time data arrives. And if you think of just a simple recurrent neural network, you can see it's essentially the same thing, right? You get these discrete updates. And so you can actually think of such models as being discretizations of a neural CDE. Okay, so I'm going to lean into the comparisons a little bit more here, in that we have these discretized recurrent or residual networks, and these have these continuous time analogs of neural ODEs or CDEs. The comparison between neural ODEs and Resnets is quite well known. You can see you can view Resnets as a discretization of a neural ODE. Okay, there's another comparison which I'd like to make, which is hopefully closer to home for some of the people here, and that's to the signature method. because one can see the signature method as being somehow doing the same thing as polynomial regression. Both of them try to write down a basis for function space, for the space of functions we're interested in, and then use that basis as a feature set on which we then do something like linear regression. So in the case of polynomial regression, we might use the monomials or Chebyshev polynomials as our basis for functions of a single scalar variable. And in the case of the signature method, we're using the signature as, in some sense, the basis of functions for functions on path space. So now if we look at deep analogs, this isn't a perfect analogy, but in some sense, neural networks fit there in that they exploit this deep compositional nature, which we observe often performs much better. And again, it's not a perfect fit, but a neural CDE somehow fits here as well, in that for a signature method, signatures are controlled differential equations. We know the signature is a very particular controlled differential equation. But rather than trying to compute this one big universal controlled differential equation, we're going to try and do something a little bit more subtle and learn a particular neural controlled differential equation. Okay, so what are some of the features? What are some of the advantages of the neural controlled differential equation model? Well, using a continuous time theory pushes this problem of messy data into the spline interpolation. It's much better suited for handling it. If we have an irregularly sampled problem, then in some sense, this is a continuous time problem. So it makes sense to use a continuous time model. From a software development point of view, you might recognize what I mean in software development language, as this is fixing a leaky abstraction. Previously, we have allowed messy data to affect our model, but now we've put this abstraction layer, this capital X, in between. For those of you concerned about the problem of informative missingness, that can be incorporated, and we're not papering over that. Another nice advantage is that this makes batching very easy. Usually when you have a regularly sampled data, you'd like to batch it together because, of course, GPUs, they perform lots and lots of operations in parallel. So you need to be able to feed it lots and lots of things in the same structure. But because of regularly sampled data, the structure depends upon the data itself. That's not quite so easy to do. But here we have this continuous time formulation. So we pre-process our data into this capital X, and then we batch the continuous time capital X together, which is now all on the same footing. Okay, next up, this neural controlled differential equation. As you can see, I've rewritten it here to look much more like a neural ordinary differential equation. I've expanded that dx into a dx ds ds. I mean, I have this matrix vector product as before between f and dx ds. So as I say, in some sense, this is an ODE. And because of that, we can actually solve it using the same tools that we already have available for neural ODEs. And in particular, we can solve it with the same software and the same code. So this is a very straightforward model to implement. Next up, because again, in some sense, it's still an ODE, then we can use that adjoint back propagation that I introduced earlier, or at least covered earlier. So quantitatively, what this means is that if h is the cost of evaluating one step of a model, for example, one step in a recurrent neural network, then normally we expect to use order ht times amount of memory, because we do h steps, so we do t steps, and each step costs h. But here, we only have to do one step at a time, which is h, and we have to hold our time series in memory, which costs t. But then because we can use this recomputation, we then only have to add these together. So this is much cheaper memory-wise. Next up, because we have this beautiful theory of controlled differential equations, which we understand quite well, then we can use this to prove universal approximation, which is one of these results which you usually want to try and show when you introduce a new model. It says that you're able to, in principle, do anything, and neural CDEs satisfy this property. And then after that, we probably wouldn't be discussing these if this wasn't the case, but neural CDEs demonstrate state-of-the-art performance. And I think for many people from a machine learning background or perspective, this is the bit that people really care about. So when I say state-of-the-art performance, let's back that up with some numbers. So this is the character trajectories data set. So this consists of people drawing characters like A, B, and C, and so on. And then we track the motion of pen across paper in order to give this trajectory in 2D space. And then subsequently we want to classify which letter have they drawn. As you can see here, to make things interesting, we've dropped variable amounts of data, going as high as dropping 70% of the data. And it turns out you can actually still find out quite a lot, even when you drop that much data. And so here we now compare the neural CDE against a variety of other models, other ODE or RNN based models, which are the broader family to which the neural CDE belongs. And these collectively represent these other models collectively represent this family, are representative of this family. And in particular, at the top there, well, think which one you're looking at, I suppose, the Ode Rnn, right, on that line, that's the model that we introduced earlier, that previous state of the art. And in particular, we see that Neural CDE outperforms every other model we consider, and more than that, it does so whilst using an order of magnitude less memory, and that's because of this adjoint backpropagation. Okay, so this is for an irregularly sampled case, and we might reasonably hypothesize that these gains go away when we consider a regularly sampled data set. So next up, we investigate the speech commands data set. So this consists of audio recordings of people saying words like left, right, yes, no, and so on. And here we see much the same property as before. The neural CDE outperforms other models whilst using an order of magnitude less memory. Now, I think it's worth highlighting here that if we look at those middle three models, that they have these incredibly high standard deviations in how well they do. And the reason for this is that roughly half the time, they just simply fail to train. Something just doesn't work. And this is a well-known phenomenon in machine learning. It just sometimes happens. We don't really, I say it's well-known, it's well observed. We don't really understand why. And in contrast, what we observe is that the neural CDE just performs consistently well. So the reason we're doing better here is really some property of the way it's trained. And we don't yet understand exactly what's going on there. So I think it's worth also mentioning that the best performing models of each class, except for that one, the GUID at the top, the best performing models of each class do actually perform comparably. So in a regularly sampled problem, I think maybe if you do things right, then you can several approaches can be made to work well. Okay, now let's be fair to the neural CDE. What are some of its limitations? What doesn't it do quite so well? So first of all is the speed of computation. Neural CDEs are something like 5 times slower than a recurrent neural network to compute. That said, we think this is largely just an implementation issue because recurrent neural networks, the ones we're using, have been implemented in C++ and they're quite heavily optimized. Whereas in contrast, the neural CDE is written in Python, and by default, it's using variable step size solvers with double precision arithmetic. And that's probably overkill for most practical problems. Okay, after that, the number of parameters in a neural CDE can easily grow quite large. And so in our previous experiments, we had to make the neural CDEs somehow small so that they had the same number of parameters. And the reason for this is that this f theta, this system in our neural CDE, is matrix valued. Recall that we had this matrix vector product between f and dx dt on the right-hand side. So what this now means is that if we have if f is a neural network and we now have some final linear map at the end of that neural network, then if the last hidden layer is of size omega and the matrix is of size VW, V rows, W columns, then this last linear layer is of size omega times V times W, so it's trilinear. And that can easily dominate the number, the parameter count in the model. We suspect this is probably unnecessary to have all of this, and that maybe low-rank approximations to f theta could be profitable. We have experimented with rank 1 approximations, but they don't perform super well. So clearly there's something to be worked on there. Okay.
Just to say you've got 2 minutes, Patrick.
Oh gosh. Okay. Well, that's quite good timing, I think. So what are some gotchas of the model? So first of all, this initial condition z that we have here, it's not just a function of the first point because we can. It's a function of the first point for translation sensitivity. The rest of the model depends on x only via the derivative of x. So if x just moves up and down, right, then we don't see any change in our model. And so by depending directly on the displacement, then we avoid that. This is also an opportunity for z to be a function of any static features as well. So if this is a medical time series, then this might be something like, say, the gender of a patient, which we don't expect to change during their stay. We must include time as a channel in capital X. The CDEs exhibit this reparameterization invariance property, this tree-like equivalence, and to avoid that, we have to make sure to explicitly include time as a channel, not just as a parameterization. And then finally, it's a standard machine learning trick to increase learning rates for later layers in the network. And the same holds true here. Since I'm running short on time, I won't try and explain why that is. So in summary, we introduce this new tool for time series, hybridizing the well-understood mathematics of CDEs with the well-understood machine learning of neural ODEs. And it has these nice advantages I've described of acting on messy time series. It's memory efficient, we demonstrate state-of-the-art performance, and it's easy to implement with existing tools. So these are the main references. The first one you're probably familiar with. The second one is the original Neural ODE paper. And the third one is really the inspiration for this paper, which was about applying Neural ODEs to time series. So we're available in the usual places on GitHub and Archive. And with that, I am done. Thank you very much for your attention.